All right, so some of you may remember kind of the partial fraction technique, some of you might not. We're going to briefly just go ahead and write down the steps that we used previously in the last unit, and then we'll use those steps on some examples. So integration by partial fractions is the process of kind of splitting up one fraction into its partial fractions, figuring out what two fractions you were adding or subtracting together initially to give you kind of a resulting fraction. So just as an example with fraction work, if you were to add two fractions together, hopefully we realize we need a common denominator. So if we multiply the first fraction by 3, we'd have 3 over 6. And if we multiply the second fraction by 2 on top and bottom, we'd have 2 over 6. So adding the fractions together, we would have 5/6. So in terms of vocabulary, we would say the partial fractions for 5/6 are 1/2 and 1/3. You can break up 5/6 into the addition of 1/2 and 1/3. So what we're doing with these integrals is we're starting with kind of the answer fraction or the resulting fraction, like this 5/6, and we're going to break it up into partial or part fractions for us to simplify this integral. Okay? So what we're going to try to do first is factor the denominator. That's kind of like your big first step. You should be able to do that. And by factoring, it's going to give us the individual denominators of those partial fractions. So can we factor that denominator? What do you guys want to do? Pull out an x. So what we're going to do is we're going to split up this original fraction into its partial fractions. We're going to use temporary numerators. We know the denominators should be an x and an x plus 1. Those are the factors. But the numerators, or the tops, we're not too sure about. So this original fraction we have within the integral can be broken up into a single fraction with the x factor in the denominator and a single fraction with the x plus 1 factor in the denominator. The temporary numerators are a and b. We're eventually going to figure out what those values are. Okay, so what we're going to try to do is think about if we were to actually add these two fractions together to get this one, we would have to take this first fraction times x plus 1 on top and bottom, and the second fraction times x on top and bottom. That way the denominators would be common, okay, just like the number example we did. So if you can imagine taking a times x plus 1 and b times x and adding those together, okay, those numerators would eventually result in the x minus 1 numerator we had from the very beginning. We're not really concerned with the denominators because we know those would all eventually be common. They would be the x squared plus x denominator we had from the beginning example. So to help us solve for a and b, we're going to strategically pick x values to plug in. That way we can figure out those temporary numerators. Is it coming back to us a little bit? Maybe it never left. That's a good thing. Can we think of some strategic x values? We want to eventually cancel out either a or b. That way we can solve for the other one. Yeah. -1 and 0. Okay, so if we plug in -1 into all the x's, we're going to have a -2 on the left-hand side of the equal side. The -1 would cancel out the a, because that factor would be 0, and then we would have a -b. So solving for b looks like we would have 2. If we plug in 0, we'll have -1 on the left-hand side a times 1, which would just be a, and then plugging in 0 for x would cancel out the b. So there's our a value. So now that we know those temporary numerators, we're going to substitute in those values, and instead of integrating the original fraction, we're going to integrate the two partial ones. So we're going to have the integral of -1 over x plus 2 over x plus 1. So these two separate ones should be easier for us to work backwards from than the one original fraction we started with. So can we think about it backwards from -1 over x? Maybe we remember Caitlin's shortcut. Caitlin doesn't remember her shortcut. That's okay. What do you think, other Caitlin?
Natural log, well, negative natural log of x. The 2 in the natural log of x plus 1.
There we go. Okay, so all of these are going to have x's in the denominator, okay, kind of signifying a natural log type process. And those temporary numerators we found are those coefficients out front. So notice how we have a -1 in front of the natural log of this denominator and a 2 in front of the natural log of that denominator. We don't know the plus, or we don't know the bounds, so we need a plus c. So there's our antiderivative. If you really felt like it, you could take the derivative of this and simplify it. You should get the original fraction back, okay, if you had time that day to do it. or you can trust yourself. Trust your gut. Okay, so we're basically just going to try a bunch more examples of these partial fractions, getting used to the setup, the solving, the integration, all that fun stuff. Okay, but the big thing is with these partial fractions is you should be able to factor the denominator. If you can't, you're most likely going to have to use a different technique, okay, integration technique. So can we integrate, or sorry, can we factor our next example? Two numbers that multiply to -10. Add to 3. Yeah.
5 and -2.
All right, so x plus 5 and x minus 2. Those are our factors, so those are our individual denominators in the partial fractions. We're going to fill in the numerators with temporary kind of a and b placeholders. So if we were to add these partial fractions together, we would have to multiply the first fraction by x minus 2 on top and bottom. So we would have an a times x minus 2 eventually. And same idea, for the other fraction we'd have to multiply by the x plus 5 denominator. So those two numerators from the partial fractions would eventually match the numerator from the original integral. So let's figure out our strategic x values to help us solve for a and b. What x, bless you, what x value could cancel out a? What x value could cancel out b? Yeah?
-5 and 2.
-5 and 2, okay. So if we plug in -5, we'd have -20 plus 41, so that'd be a 21. And then we'd have a -7a, but -5 would cancel out the b. So solving for a looks like we'll get -3. If we plug in 2, 8 plus 41 would give us 49. Plugging in 2 would cancel out the a, and then plugging in 2 would give us a 7b. So solving for b looks like we get 7. So with these temporary numerators that we now found, we're going to integrate the two partial fractions to figure out the antiderivative of the original fraction that we had. takers? Yeah.
Negative 3 times the natural log of x plus 5 plus 7 times the natural log of x minus 2.
There we go. Plus C, good. How'd you do? Pretty good? All right, let's try another one. You should be able to factor the denominator. If you can't, we're going to have to go about this using a different integration technique. So, can we factor the denominator? Looks like difference of squares. We'll have x plus 1, x minus 1. Temporary numerators. If you were to actually multiply those partial fractions together, we would have an a times x minus 1 and then a b times x plus 1 showing up in the numerator. And that should equal the original numerator. Strategic x values. Thinking 1 and negative 1? You guys are on a roll. I can see the laser focusness. I'll just show the work and you guys check it. Is that better? Okay. How'd you do? Pretty good? Did anybody rewrite it differently? Maybe not. Okay, we're going to make note of this. Okay, do you guys notice how the a and b value were basically the same number, right? One's positive, one's negative. Okay. What if I were to reorder these? For instance, 3 natural log of x minus 1 minus 3 natural log of x plus 1. Okay, so remember the 3's are technically the same value, right? If you are subtracting 2 logs together, notice how they have the same coefficient, that's kind of key. If you're subtracting 2 logs together, can we use a property to simplify it? Yeah.
Would it be 3 out of would be x minus 1 over x plus 1?
You were originally dividing the insides of those logs. Yep. Okay, that one's a little tricky to notice because you had to reorder it to figure it out. But whenever you have basically the same a and b value, the same coefficient, you could most likely use a property of logs to simplify or rewrite it. Okay, probably worth noting because, for instance, I don't know if it was a multiple choice question. This is maybe what one of the answers looked like and not that. Okay, so just getting used to rewriting in a different way to let your answer match one of the options. Okay? All right, let's try 5. Can we factor? This one's a little tricky because you have that coefficient of 2 in front of the x squared. Can we get 2x minus 1 and x minus 1? Does that work out? Alright, so if we were to multiply those, or if we were to get a common denominator on those partial fractions, we'd have a times x minus 1 and a b times 2x minus 1, and that should equal the original numerator. Bless you. Strategic x values. Looks like 1, and then the other one would be a half. What do you guys think for your antiderivative? Can we get negative 2 and 1 as the A and B value? Okay. Any takers? Brave soul. Go, Caitlin.
Natural log of 2x minus 1 minus 2 natural log of x minus 1.
All right, plus C. All right, let's check this out. This one's a little tricky, okay? We know that if we were to take the derivative of these two, we would get the two fractions in the integral, right? So if we were to take the derivative of this guy, we would need 1 over the inside times the derivative of the inside, right? Because we have that chain. So notice how when that happens, we have 2 over 2x minus 1. That doesn't exactly match what we have here. But it's kind of close, right? We're off by a multiplier. We need something else out front. What do we need to multiply to kind of cancel out that 2 there? Because notice how if that 2 wasn't there, we would have exactly what we wanted. Yeah?
1/2.
A 1/2. Okay, so what's actually happening is you guys are used to having that coefficient coming from the numerator. Where's the 2 coming from? The denominator, that coefficient in front of the x. Okay, so notice how the same thing's basically going on here. We have a negative 2 over 1, right? And that's our coefficient out front. It's a little tricky to catch, but if you do have a coefficient on the x in the denominator, that's being included in that coefficient out front. Do you see that? A little tricky, okay? So we would have 1/2 natural log of 2x minus 1 minus 2 natural log of x minus 1 plus c. There's your antiderivative. All right? We're not going to finish the next one, okay? I'm just going to get you guys hyped up for tomorrow. Can we factor the denominator? Yes. How? You could pull out an x. Oh, yes, Abby, I saw that. No, she said no. Yep, we're going to have 3 of them. All right, you can pull out an x. That's one factor. Oh, I'm getting you hyped. We're like, I can't wait for tomorrow. So you can pull out an x, and then 2 numbers that multiply to -6 add to 1. We'll have x plus 3 and x minus 2. So what do you think our temporary numerators are going to look like? ABC. Do you guys want to keep going, or do we want to stay hyped for tomorrow? Let's keep going? We'll try it. Okay, guys, if we know that this is going to equal the original numerator, so we might as well just go ahead and write that down first. But if we were to try to get a common denominator on all three of these, what would you have to multiply the first fraction by? X plus 3 and an x minus 2. What would you have to multiply the second fraction by? X and x minus 2. Do you notice how it's basically the other denominators that fraction doesn't have? And then the last fraction, we would need an x and an x minus 3. Oh, sorry, x plus 3. Good. Alright, so we'll stop there. Maybe you guys can think of strategic x values, but we'll see how this kind of triplet one works tomorrow. Just a cry. Zoe.
Hope for the best.